Okay, good afternoon, everyone. This work was done in collaboration with Stephen Dowd, my PhD student, and thanks Tanya and Boonabadine for inviting me to talk here today. Okay, so we've heard a lot about Koopman today. I'll just give a quick high-level overview. Often we're dealing with some sort of dynamical system given by xk plus 1 equals f at xk comma u. What's really exciting about the Koopman operator is we can lift the system, okay? And in this lifted space, we can get a linear model. Okay, so that's really, really exciting. Oh, I got this thing, yeah. Okay, that's really exciting. Because of this linearity, we can do things, in particular, what I'm interested in is control tasks. Okay, I'm interested in designing controllers, okay? But as we talked a lot about today, there's also other things you can do with the Koopman operator. You can look at its spectrum or its frequency response and you use it for prediction. But in particular, me, coming from the control systems community, I've been very much interested in using the Koopman operator for control as well as navigation. Okay, so high-level overview of what is the Koopman operator. Okay, so say we have some sort of discrete time nonlinear system, xk plus 1 equals f as a function of xk. Okay, and in the, and in the upper right here, we can think of this. Okay, so we have some sort of state space where we can go from xk through f to xk plus 1. Okay, so now we can have this Koopman operator, which maps h to h. H you can think of as like L2, where we have these so-called lifting functions psi. And using the Koopman operator, we can write like this in equation 2, where u is often, most often infinite dimensional. So we now think of this diagram over here. Now in practice, when we're working with real data, we're often going to approximate the Koopman operator and work with a Koopman, I like to call it the Koopman matrix, okay, so this matrix U, where we have all these lifting functions kind of stacked up. We can go from lifting function as a function of xk through the Koopman matrix to lifting function as a function of xk plus 1. So we can kind of think of this approximate space here, okay? Often because of truncation, we're going to have a little bit of error. And so one of the strategies when trying to identify the Koopman operator from data or when I'm trying to identify the approximate Koopman operator from data, is we want to minimize those residuals. Okay. Okay, so let's talk about inputs. I'm often dealing with systems that have inputs. So an input is defined as UK, all right? So in this case, what we're going to do is we're going to partition the lifting function in a particular way. We're going to have the lifting functions partitioned to this theta part, which is a function of only x, and this new part, which is a function of x as well as u. And then we can do some data-driven stuff, and we can basically extract a Koopman operator that has two chunks, an A and a B part, where this A is related to theta, and this B is involving the input. And again, we might have some sort of residual there, some residual error because it's a finite approximation. Okay, good stuff. In a little bit more detail, how can you find the Koopman operator from data? Okay, so what we can do is we can take a bunch of data. Okay, so we have this data set. We can form these snapshot matrices here. Okay, so here are some snapshot matrices psi. We have the shifted snapshot matrices given by theta plus. Okay, and then what we want to do is we want to find the Koopman matrix, this U, that basically minimizes the residuals. Okay, so this is basically a least squares problem. And we can solve for the Koopman operator that minimizes those residuals. Awesome. A little bit later in the talk, we're going to be using extended DMD. Okay, so let's talk about extended DMD a little bit. So extended DMD is a really clever trick. At the undergraduate level, I teach numerical methods, and I like to tell my students the oldest tricks in the book are add 0 or multiply by 1. And I really think of eDMD as this multiplying by the identity matrix. So basically what you're doing here is you're jamming in the identity matrix here between these two matrices. And then if you redefine, or if you define, I should say, G and H as shown in equation 14, you actually get some much smaller matrices. In particular, H is much smaller dimensionally, which is easier to compute the inverse. So DMD is a clever trick. Okay, so what motivates this talk is the fact that many systems do not operate in open loop. They operate in closed loop. So let's just make sure we're all on the same page between open loop versus closed loop. So when I say open loop, there's some sort of dynamical system. Okay, you can think of like x dot equals f of x, comma u, and y is equal. You could have just like linear measurements. So you have some sort of input, there's some sort of state space thing going on here, and you get some outputs. So u to y. So that's an open loop system. And many data-driven methods basically are for open loop systems. What we're talking about today is when you have a feedback loop. So you might have some sort of controller, I'm just going to call it C. You still have some sort of dynamic system. Okay, so y is equal to whatever, some function of x, doesn't matter. It goes some measurement, and here's the key part, you have a feedback loop, okay? And this C thing here, this thing is not static. It's almost always dynamic, okay? In the world I live in, it's always going to be dynamic, okay? And so what this talk is motivated by is how do we leverage this amazing thing called the Koopman operator, okay? But when we have feedback, a little bit of a mic drop there, literally. Literally mic drop, unintentional. Okay? So that's what this whole talk is about, is I live in that world, okay, where there's feedback, okay? And in particular, there's some systems where you cannot operate that system without a feedback loop, okay? So let's take this XV15, okay? So, you know, these guys at NASA, they have this sweet finite element model, okay? They want to validate the finite element model, okay? They can't validate the finite element model without flight data, but you can't get flight data without a controller, okay? So you have to fly this thing with a control in the loop, and in particular, like I've talked to guys at Boeing, and I've talked to various people, and this is literally what they do. They will come up with a preliminary controller that basically works. It's not going to be great performance or whatever. They'll get a controller that just works. They'll go out, fly the aircraft, they'll get a ton of flight data, and then they want to basically come up with a data-driven model to then validate their FEM, okay? So that's what this talk is really centered around, is how do we do that, okay, but in a Koopman framework, okay? So how do we actually identify, in some sense, the underlying Koopman model of that aircraft, but using data that has a controller in the loop, okay? That's the key thing here. We cannot get pure open loop data. We can only get closed loop data. All right? That's the problem we're solving here. I want to give credit where credit's due. This is very much motivated by what's done in what's called the subspace identification literature. I come from the systems and control community, and system identification is a very old field. And so what I'm talking about here is very much similar to this type of approach called subspace ID. Okay, let's keep on going. Okay, so here's a very high-level overview of what we do. So here we have a closed loop system. Okay, so what we're after is a Koopman representation of the plant. Okay, we're going to assume that we actually know the controller we've applied. That's a reasonable assumption because we designed it. Okay, we picked the gains. Okay, now what we're going to do is we're going to have references which we designed. We're going to collect a bunch of reference data. Okay, we're going to assume we have access to the control information, so the states, and we have some measurements. Okay. And just, as I said, this is what we know. We know all this stuff here, but we don't know the Koopman representation of the underlying plant. What we're then going to do is we're going to lift this in a closed loop sense, okay? Then we're going to basically identify a closed loop Koopman representation of the system, but we're going to have some constraints in there, and I'll show you why. And then from that identification procedure, we can actually extract out the underlying Koopman representation of the system, okay? So that's a high-level overview of what we're doing. All right, so let's get into the weeds a little bit. Okay, so we have some sort of Koopman representation of the system, okay? We're actually trying to find AP and BP. That's what we're actually looking for. We're actually going to know, we're going to assume that the C and the D matrices for that Koopman model are of exactly this structure. This is somewhat restrictive. It basically means that we can access certain states directly, okay? This is our controller. You can think of this as any type of controller you want. Yesterday, there was someone who mentioned PID control. You can be a PID controller for example. And in fact, later on, I'm going to deal exclusively with PID type structures. Okay, so that's the plant and the control. This is an open loop type structure with the control involved. So here what we have is we have some sort of UC goes into a controller. This is some sort of feed forward to control type signal that then goes into our plant, okay? And I'm going to define some intermediate variables here. I'm going to say the input to the plant is this, which is the output of the controller plus F, and also have some intermediate variables here as well. Okay, so now the next key step here is now I got to close the loop, okay? Before I do that though, let's just make sure we understand this open loop structure. So this is the open loop structure involving all of our state space matrices. And it's a little bit of a busy slide, but the punchline here is this open loop structure involves the controller parameters, so like, AC, CC, but as well as the plant parameters like, PB and AP here. And we're after these things at the end of the day. That's what we're after, okay? Now we close the loop. Okay, so we're gonna close the loop. And we have some intermediate variables. Okay, so this is basically some sort of tracking type error. And then we have also some sort of input. Okay, so we close this loop and now we get this big complicated system. Okay, so this is a closed loop system, okay? So now, in some sense, we have tools to deal with this. And what we're gonna do is we're basically going to identify this closed loop system. So now we can think of having the inputs being R and F. We have some sort of measurements here. What we're trying to identify is AF and BF collectively. And then the whole trick, okay, the whole trick here is if we have AF and BF, can we somehow extract out basically the AP and the BP, okay? And that'll be the Koopman representation of our underlying model. All right, so that's the whole strategy here. There's some conditions on well-posedness and yada, yada, yada that will be satisfied if you have no feed-through term, and that's a standard thing if you ever dealt with feedback loops. Okay, so this is how it works. So basically at the end of the day, we use some variant of EDMD, okay, to identify the closed loop Koopman operator, okay? So let's give it in equation 29. So here's this closed loop AF thing here, this closed loop BF. This is really not convenient, is it? We're gonna go old-fashioned. I'm tall. We're gonna identify this thing from closed loop data, okay? And as I've been saying, we really want to extract out AP and BP, okay? By the way, it's the hook on this one. So next time someone goes over, you can hook them, Okay, so now we have these relationships here, okay? So we see that we have this U22, which involves AP and BP, which is our after. But also we have this big long expression, which we can extract out basically from matching some terms. Okay, so that to that would be this term, that to that would be that term, et cetera, et cetera, et cetera. Okay? And the problem we now solve is we say, okay, find us basically this closed loop Koopman matrix here. So we're basically trying to find this thing, all right? But we have some constraints, okay? So we have to explicitly enforce this constraint, okay? Because basically the BP shows up in a bunch of spots, as well as the BP and the AP are coupled through that U22, okay? So through that term. Okay, so we have a constraint here, okay? All right, so that's what we do. Now there's some caveats here as well, not caveats, there's some extra things I gotta talk about before we go on. So often we're gonna add in this regularizer here, okay? So this regularizer basically penalizes insanely large values of the approximate Koopman operator, and that's a pretty standard thing we're gonna add in. Also in full disclosure, this was not the first cut at this problem, okay? The first thing we tried was just solve that problem without any explicit constraints, okay? So to solve that for this big Koopman matrix, and then try to basically extract out the A and the AP and the BP, so extract out that and then that. And the naive way we did that, and I'm gonna call it the naive way, is we basically just took this equation, did some sort of pseudo inverse over here, and notice this is a wide matrix, okay? So it has a null space, right? So this is not gonna be unique, okay? But we did some pseudo inverse, mumbo jumbo, and then we extracted out the AP, and that was the naive approach. And a little bit later in my talk, I'm gonna show you that the naive approach doesn't work, and really, you gotta do this. You have to add in these constraints explicitly when you're solving for AP and BP. Okay, let's keep on keeping on. Whoopsies. Okay, so let's start simple. Let's start in simulation. Just to test things out, so let's consider a Duffing oscillator. Okay, so here's our Duffing oscillator. These are the dynamics, all right? And we're just gonna add in a really simple, what's called proportional integral controller. Okay, so we generate a bunch of data in simulation. Then we take all that data, we're gonna run it through some lifting functions. We're gonna use these lifting functions here. Okay, so we're gonna involve these radial basis functions as well as some delays. Okay, and those are the parameters we used. So here's the results we get. Okay, so let's focus on the left side first. So this is closed loop EDMD, so that's the approach that I'm proposing, okay? And we see when we have our closed loop EDMD approach, this is error, okay, so this is prediction error. It works pretty good when we're working with this closed loop system, so that's great. I'm gonna compare it to a closed loop autoregressive exogenous input model. This is a very classic type of system identification model from the 1970s. And we see that it does not perform so well because it's strictly linear versus our approach uses Koopman and it can handle nonlinearities. Okay, so that's looking good. Now let's move over to the right-hand side here. So this Duffing oscillator is actually asymptotically stable. So if we wanted to, we could actually ID things in open loop if we wanted. So that's what this ARX and EDMD is. EDMD is a standard EDMD identified in open loop. Okay, and what we see is that our proposed approach and standard EDMD perform about the same. Okay, and then the ARX methods don't perform that great, basically because they're not capturing the nonlinearities. Okay, so this is basically saying, yeah, your proposed method works, great, but this is not really saying that it beats EDMD. Okay, so now let's go to a more complicated example to look into, like, yeah, is this really better in some sense, and in what sense is this a better approach than just standard EDMD? Okay, by the way, the hook is actually kind of annoying, so I'm going to put that down and pick up the other one. Okay, so now let's actually go to a system that's actually open loop unstable. So here we have the inverted pendulum, and we want to stabilize. Oh, that's convenient. Didn't plan that. We want to stabilize like this, right? We want to be able to stabilize the inverted pendulum. You can't do that with a closed loop controller, all right? So yeah, we are going to collect a bunch of data from this inverted pendulum system where we have a controller working in closed loop. This is our controller, okay? And we want to actually flesh out, when does our proposed method, closed loop EDMD, actually outperform this standard EDMD? Okay, that's what we want to do. Okay, full disclosure, all the plots coming up, there's some nuance to this, and I'm going to be going back and forth a little bit. I'm sorry, but that's what we're working with. Okay, so first things first, let's start on the right. Okay, so I've run my algorithm. I get a closed loop Koopman operator. I can extract out the underlying A matrix associated with the plant, like the Koopman A matrix, if you will. And what would we expect? Like this inverted pendulum system, if you linearize, forget linearization, it's unstable, right? It's an unstable system. You don't have any control. It's going to diverge, basically. The angle theta is going to diverge. So what we see here on the right-hand side is if we look at the spectrum of the A matrix associated with the plant, okay, we see if we have low regularizer coefficients, okay, low regularizers, like, alpha is like less than 1, we get what we'd expect with our closed loop EDMD method, which is to say, yeah, we have at least one eigenvalue that is outside the unit circle representing instability. So that's looking good. Now let's compare it just to classic EDMD. And when I say classic EDMD, what I mean is it's like I'm ignoring the control. Like I just measure, I just measure this and this, and I apply EDMD, just naively thinking this is not here. Okay? That's what I mean. So EDMD actually does the right thing as well. Is for low regularization coefficients, it actually gets an unstable system too. Okay, that makes sense. Now what about the closed loop spectrum? So this is the eigenvalues of AF. So this is the closed loop A matrix. And my controller, I only collected data when my controller was working, was actually stabilizing the system, okay? So we expect for any regularizer that the closed loop A matrix should have all its eigenvalues inside the unit disk, okay? If we look at our closed loop method, okay, the blue line, that's exactly what we have. Sweet, for any regularizer coefficient, okay? Unfortunately, if you look at EDMD, which is to say, I just pretended I didn't have something in closed loop, so I basically, I kind of put the blinders on. I said, yeah, I'm just going to collect some data here, run EDMD, and then wrap a controller around it. If we have too big a regularizer, okay, we actually get an unstable closed loop. So that's not good, okay? So already we're seeing some benefits of the closed loop method is that if you don't know the regularizer, alpha, okay, the regularizer coefficient, I should be saying, then at least our proposed method, closed loop EMD, is going to get you something that makes sense in closed loop. That is, all the eigenvalues associated with the closed loop system are going to be inside the unit disk. Okay, let's keep on going. Let's further investigate pros and cons of just kind of a naive approach relative to this closed loop EDMD. Okay, so now let's talk about scoring, in particular scoring predictions. So we're going to actually use the R-squared score, also called the coefficient of determination. Okay, so it's defined here as equation 39, where this is the mean. Basically what we want, once we've learned a model, is we want an R-squared score of 1. That basically means perfect predictions. If you get predictions that capture the mean of the data but don't capture the nuances, you're going to get R-squared score of 0. And if you have terrible predictions, R-squared can be arbitrarily negative. Okay? So yeah, let's see how our methods compare in terms of an R-squared score. Okay, so again, let's start over on the right here. Okay. So what this is showing us is that, again, if you just put the blinders on and you didn't consider the closed loop system, what would EMD do to get an acceptable R² score, it would want to have a super high regularizer. It would go up, and because it wants to get this up to close to 1, okay? But we know that's not really what we want, right? Why? And again, I apologize for bouncing around a little bit. We don't want a super high regularizer. Why? Because then we are not capturing the unstable properties of the open loop system, and we're going to get an unstable closed loop. That's not what we want, okay? Now if we go over here and we look at our closed loop method here, okay, so this is the R² scores of the closed loop system identified using either closed loop EDMD or EDMD. We see our closed loop method is much more robust to if we pick the wrong regularizer, basically, okay? So that's good news there. What this is this is again taking the standard, blind EDMD, then wrapping our controller around it. And for low regularizer coefficients, it actually kind of makes sense. It actually gives pretty good predictions. But then it just dives off to negative infinity. Well, why is that? Is again, what's this R² score thing? It's a measure of how good is the prediction. Well, in closed loop, you're doing terrible predictions when you have a high regularizer because it goes unstable, okay? So that makes a lot of sense. Okay, these are eigenvalue plots, basically, okay? And in particular, these are actually now optimal regularizing coefficients. So what I'm actually plotting here is the eigenvalues associated what would be the best regularizer coefficient. So think of that, like this value of alpha there for this method, this value of alpha for this method, and then this value of alpha for those two methods. That's what that's showing. And what we see here is, here's the punchline basically, is first of all, the proposed method closed loop EDMD does exactly what you expect. In closed loop, all the eigenvalues are inside the unit disk. But then if we look at the open loop plant, we definitely have an eigenvalue outside the unit spectrum, which is exactly what we expect, okay? Because like, again, if I turn off the controller, just turn it off, it's gonna go unstable. Okay, so that's what that's predicting. But also what we're seeing here is things like this one right here, which is if we pick that regularizer according to the R² score, and by the way, this is all in the context of hyperparameter optimization, like we're doing some like Bayes op or something like that to find the optimal hyperparameters, you actually end up with an unstable closed loop, which doesn't make any sense, okay? Next, these are again some time domain error plots, okay? So here on the left, we again get some things that make sense. So for example, in closed loop, our proposed method, it's it's bounded responses, okay? Versus if we did this kind of silly EDMD way, like just put the blinders on, do EDMD, then wrap the controller around it, we get an unstable response. Over here, there's a case where we actually want instability. Again, if we just turn the controller off, our system should be unstable. So this is actually what this shows us, is that we get an unstable response in the open loop plant, as if we turn the controller off. Yeah, so that's what that's showing. Okay, so now I gotta pause for 1 second. So you remember how I said earlier on that this method I'm proposing that has these constraints was actually not the first one we tried. We tried this kind of ad hoc method where we tried to back out some parameters just by inverting a matrix. So now I'm gonna talk about that. So when I say reconstructed, what I mean by that is we've identified the closed loop system, we extracted the controller parameters, but we did not enforce that constraint directly. And then we rewrapped the system with a controller. If you don't put in the constraints explicitly in the optimization problem, you get this problem happening, which is to say, I identified the system, I took out the controller to like basically look at the plant, then I put the controller back in, but when I put the controller back in, I actually get an unstable system. And it's pretty subtle what's going on here, but at the end of the day, if I go, I don't want to go back. At the end of the day, the reason why this happens is there's not a unique solution to backing out those controller parameters when you're not enforcing that constraint explicitly. Okay, so that's what's going on here. So again, this is another pro, if you will, of the proposed method that involves that constraint, is that you're always enforcing that constraint explicitly, which is to say the identified model has to match the AP, the BP as well. Okay. Yeah, so what this is basically saying is if you do it properly with the constraints in there, you're going to get a bounded prediction error, which is what you want exactly. Okay, coffee breaks next. Don't want to keep anyone away from coffee. I sure don't want to be kept away from coffee. So this is a summary here. Okay, so ARX, autoregressive exogenous input modeling, it's a linear method. It's from the 1970s. Honestly, it's not a bad method, but unfortunately, when you use it kind of naively, you might get bias in your estimates, okay? And it also doesn't work for nonlinear systems. We have various versions of EDMD, okay, which were all in those plots, okay? And at the end of the day, if we just get to the punchline, the proposed method we're proposing, it gives us a bounded R2 score, it uses the regularizer properly, it avoids bias, and it works directly with nonlinear systems. All right, great. Okay, so my student, Steven, who's in the audience here, he's an absolute amazing programmer. He created this thing called PyCoop, and everything I talked about today and much, much more is in PyCoop, which you can just go to our GitHub page and just pip install, and away you go. So thank you, Steven. And let's just wrap this up. So yeah, the Koopman operator is super amazing, super exciting. Why? Because we can represent nonlinear systems in this linear fashion, okay? And in particular, when we're working with data and all the problems I work on, I'm going to use a finite dimensional Koopman operator, okay? What this talk was really about is leveraging some ideas from the subspace identification community to identify a Koopman representation of a system using closed loop data, okay? So now we could do things like, go fly an aircraft, collect a bunch of data, run this algorithm and extract out the actual underlying aircraft dynamics and go do things like compare it to like a finite element model or something like that. Moreover, we actually tested this out on an actual real inverted pendulum system in the lab, which is pretty cool. I want to acknowledge my funding sources. Thank you very much, all these funding people. And if you would like to read the paper, it's just been accepted. So you can hit that QR code and see the paper if you want. Thank you so much.